This is Atanak Yıldız from Sabancı University. In this presentation, I'm going to introduce Gosh, embedding large graphs on small hardware, which is written by myself, Amr Alapsi Alhundi, and Kamer Kaya. Gosh provides ultra-fast embeddings on a single GPU for any arbitrarily large graph. It is ultra-fast thanks to a parallel novel coarsening algorithm, which has a small overhead. Gosh's flexible and dynamic task scheduling for memory-restricting devices enables Gosh to embed any arbitrarily large graph as stated before. Below, you can see a comparison between the state-of-the-art algorithms and Gosh. Gosh is able to provide comparable AUC or OC scores while being 26 to 27 times faster than the state-of-the-art. Graphs can be found everywhere from protein-to-protein interaction networks to social networks. As time passes, graphs only get bigger. And nowadays, we can find graphs that have up to tens of millions of vertices and billions of edges, which requires a lot of time to train. Various machine learning tasks can be applied on graphs. Most popular are link prediction, node classification, and anomaly detection. For this work, we evaluate Gosh on link prediction, and we leave node classification and anomaly detection for future work. For graphs, connectivity information is highly unstructured, and this is not suitable for machine learning tasks. The process of graph embedding transforms this unstructured data into a standard d-dimensional representation, which is way more suitable for machine learning tasks to learn from. Although it is way more suitable, graph embedding is not cheap. It requires hours of CPU time for graphs with hundreds of thousands of vertices, and even larger graphs could require days. To tackle this problem, one can utilize distributed systems, GPU parallelization, and graph coarsening approaches. Before delving more into Gosh, I would like to make some definitions. Graph embedding is the process of creating the embedding matrix M with vertices amount of rows and dimensions amount of columns, where the vector MV or MAMB, as in the figure, is the embedding vertex of A or B or C. What is graph coarsening? Coursing a graph GI into the graph GI plus 1 will give every merged group in GI a supernode in GI plus 1 and transfers the edge information from the sub to the supernodes. For example, in this figure, the blue vertices are merged together, the yellow vertices are merged together, and the edge information is updated accordingly. Gosh algorithm starts by coarsening the input graph into smaller and smaller graphs until some ending criteria is met. This can be seen as in left of the figure, where G0 is coarsened to G1, and G1 is coarsened all the way through to GD-1. Then, the smallest graph will be embedded, and its embeddings, MD-1, will be projected to the previous level by setting the embedding of every node in the finer graph, MD-2, to the embedding of its supernode in MD-1. This process continues until the original graph G0 has been embedded and M0 is obtained. The embedding procedure of Gosh employs the process of noise contrastive estimation through stochastic gradient descent. For all the epochs, and given an epoch for all the vertices in the graph, we do a positive update, and then NS negative updates. In order to do this, one needs to store the embedding and the graph in the GPU memory. But this is a memory-intensive process. A social network with 100 million vertices and a standard embedding dimensionality of 128 would require around 50 gigabytes of memory with using single precision. This is way above the capacity of any contemporary GPU. For this problem, Gush proposes a specialized embedding algorithm for large graphs. Gush partitions a large graph into smaller subgraphs that can be processed by a single GPU to embed the whole graph in rotations. For the multi-level setting, each level of graph should be checked whether it fits in the GPU or not. If it does, a single kernel embedding job is dispatched to the GPU. If it doesn't, the large graph embedding procedure is used. And for the multi-level setting, another question arises. How do the epochs get distributed across levels? Embedding the coarser levels is faster and accounts for more updates because these updates are projected through the levels. But updates to the finer levels create more finely tuned embeddings. Gush employs a hybrid work distribution approach in which a portion P of the epochs is distributed evenly across the levels, and the remaining epochs are distributed geometrically such that coarser levels get more epochs. Then let's talk about the embedding step in the GPU. To maximize GPU utilization and minimize race conditions, Gush employs a one update per GPU warp approach. As seen in the figure, consecutive vector locations are updated through consecutive threads in the GPU warp, which employs a coalesced access on the embeddings. But this creates a problem. For smaller dimensions, especially dimensions smaller than 16, the previous method, one warp per one vertex update procedure, will result in 32 minus d threads to be idle at any time. For this, Gush employs a specialized method for such a case, where groups of multiples of 8 and 16 threads are responsible for a single vertex. So if the dimension is smaller than 8, 8 threads will be responsible for a vertex update in a warp. If it's smaller than 16, smaller than 16 and bigger than 8, then 16 threads will be responsible for an update. With graph coarsening, we aim to create an approach that will produce the best coarsening effectiveness and best coarsening efficiency. So one may ask, what is coarsening effectiveness and efficiency? Coarsening effectiveness is measured in terms of how well the resultant embeddings perform compared to other coarsenings. So with effectiveness, we actually compare the AUC ROC scores of different coarsenings that goes through the same embedding process. With coarsening efficiency, at some level I, we measure the rate of decrease in the number of vertices from level I-1 to level I. In other words, with efficiency, we measure how well we can shrink a graph throughout the levels. To start multi-edge collapse, first we sort the vertices in descending order based on the number of edges. This prevents hot vertices from being matched early on in the coarsening process. Then, we process this sorted set sequentially. If a vertex V is not yet marked, we mark it to be a new supernode V prime and match any of its unmarked neighbors by marking them as V prime as well. V prime will be the super vertex in the coarser graph. But doing this, we have another heuristic, which is called the matching criteria. A vertex V cannot mark a vertex U, and vice versa, if both U and V have more edges than the average number of edges per vertex in the graph. This rule prevents two hot vertices from being coarsened into a single supervertex, and this highly increases the coarsening efficiency and effectiveness. As you can see in this example, we start with B, which has the highest degree in the graph as 3. B is matched to A and C, and A, B, and C are marked. We cannot match B to F because F has a higher degree than the average degree of the graph. Then F or E should be processed because they both have two edges. Randomly, E is selected and D is matched to E, and they both are marked. Finally, we process F, but all of its neighbors are marked, so we cannot merge F or match F to any other vertex. So in the resultant graph, we have X, Y, W. X represents ABC, Y represents F, and W represents D and E. Multi-edge collapse has a space and time complexity of OV plus E and has the potential of parallelization. For parallelization, we have two different phases, where the first phase is the matching phase. For matching phase, we process vertices in parallel using T-threads, but place locks on every vertex which the processing threads must acquire before marking or matching. The locks are essential for this phase because we need to guarantee that a vertex cannot be matched by two different vertices. Second is the reconstruction phase. When reconstructing the edges, every thread from T-threads will reconstruct the edges of a range of supervertices. Afterwards, the edge information generated by the threads are merged sequentially in OT time. Unlike the matching phase, for this phase, we don't need any locks. We partition the embeddings into smaller parts such that 3 parts can fit inside the GPU concurrently. Then, we execute batches of small jobs, each of which carries out updates between the vertices in 2 parts. So in the figure on the right, we have 3 jobs on the GPU. And at a given point in time, we would update the part P0 and P1, or P0, P4, or P1 and P4. For a single rotation to be completed, every possible pair of parts should be executed. When a part is used up on the GPU, it is switched out for another one from the CPU. As you can see on the figure on the left, when embedding of P4 and P0 is done, P0 is switched out with P2, and the embedding of P4 and P2 is executed. Another partitioning that we do is sample space partitioning. Storing the graph on the GPU is expensive. Therefore, edges are sampled on the CPU concurrently with the embedding and sent to the GPU. For example, when we have the parts P0 and P4 in the GPU, we need to have the sample 40 in the GPU in order to do the updates. The GPU will store 3 or more sample pools on the GPU, and the CPU will bring new sample pools depending on the running embedding. So the samples are generated in the CPU and then transferred to the GPU. You can see a high-level look of the workflow here. We have 3 concurrent tasks on the CPU and another one in the GPU. The samplers are a team of CPU samplers concurrently generating positive samples. Pool manager, a CPU thread that will dispatch copies of sample pools to the GPU. The master thread is responsible for copying embedding parts and dispatching embedding kernels. And finally, GPU kernels. They are the jobs that execute the embedding jobs.
As stated before, we use link prediction as the machine learning task to evaluate our model, and we use AUC-ROC as the metric. The evaluated systems are Gauche, Verse, Graphite, and Mile. For Gauche, we have 4 different versions: fast, normal, and slow version, where we tweak the smoothing factor and epochs and learning rate to demonstrate the flexibility of the model. The final version of Gosh is Gosh No Coarse. For this version, we directly do embedding without coarsening. We select verse because Gosh is based on verse and it's a multi-core CPU implementation. We select Graphite because it's the state-of-the-art multi-GPU implementation. And we use two different settings for Graphite as well. A fast and a slow setting where we have two different epochs. The last tool we selected is Mile. We select Mile because it also applies coarsening. As seen in the table on the left, we use 12 graphs to evaluate. 8 graphs which are relatively smaller and 4 graphs which are relatively larger. The largest graph that we have is Confranster, which has 65 million vertices and 1.8 billion edges. We use the embeddings to train a logistic regression model. 80% of the data is used for training and 20% of the data is used for testing. Rows in the training and test sets are edges, where 50% of those are positive and the remaining are negative. The row of edge UV, either in the training set or the test set, is constructed by element-wise multiplying the embeddings of U and V. To evaluate the coarsening efficiency of Gosh, we can compare Gosh to Mile. As can be seen in the table, Gosh is orders of magnitudes faster, where for this graph, Mile took 1,300 seconds to coarsen, where Gosh took just 6.6 seconds. Also, Gosh has better coarsening throughout the levels, where we reduce the graph from 3 million vertices to 275 vertices, and Mile can only reduce it down to 12,000 vertices. And Gosh also has a better prediction accuracy, which is shown in a later slide. Here you can see the speedup breakdown of Gosh. As a baseline, we use a multi-core CPU implementation. A naive GPU implementation actually degrades the performance, which emphasizes the importance of good GPU coding. Actually, the optimized, carefully implemented GPU version can have speedup over the CPU baseline, where the speedup can be up to 9 times. Introducing coarsening to the equation drastically improves the performance. Where previously it was 9 times, now with coarsening, we can speed up the process up to 90 times. And the parallel coarsening version of Gosh is especially important for large graphs, where the coarsening overhead is relatively large. Here, we show the medium scale graph comparison between other tools. We maintain the accuracy while being faster than the other models. And also, with our fast, normal, and slow version, we show flexibility between speed and accuracy. For large-scale graphs, we can only show the result of verse on sockets available. This is because Graphite cannot run large-scale graphs using a single GPU, and Mile and verse time out after 12 hours of runtime. As seen in the table, introducing a small dimensions optimization makes a difference. When d is smaller than 32, assigning a single update to a warp is a waste of resources, because 32 minus d number of threads will remain idle. Hence, we assign 32 divided by d updates to a single warp to fully utilize all the GPU cores. To conclude, Gosh provides high-quality embeddings using minimal hardware and at a fraction of the time. It employs a novel parallel coarsening algorithm and a special scheduling schema to embed large graphs using a single GPU. And with our experiments, we show the power of Gosh and also the flexibility between quality and speed with different versions of cache.